Hello, everyone, and welcome back to the session on Python for data science. I really hope you've had a lovely lunch. It's a lovely day, and I hope all of you are staying safe, staying at home, being isolated. This is an important time, for all of us, for everyone in India. It is an essential time for us to really be safe, be socially distanced, and take care of yourselves and take care of your families. So I hope you've had a lovely lunch, and we'll now be starting with what we call as NumPy. And NumPy is also called as numerical Python, which is basically a library in the Python programming language that's used for doing numerical computations. So it could be numerical computations for purposes of you want to take in data, you want to take in matrices, you want to arrange these matrices differently, and you can have data of various structures, which is a one-dimensional array, a two-dimensional array, a three-dimensional array, etc. So there are various types of dimensions of data, and I think we'll cover some of this today on why do you need 2D arrays. And a simple example of 2D array is it is essentially data in a row column form, right? And that's one of the ways and one of the uses of a 2D array. But you could also have 3D arrays, and 3D arrays are essentially nothing but, an example of a 3D array is images, wherein you have a pixel, which comes in row and column coordinates, and then you have the color of the pixel, which is actually the Z coordinate, which is the third dimension in the array. So it's time we start handling all of this image data, video data, generally structured data, perform basic operations on the structured data. So this session might be a little heavy in terms of numerical, computation, statistical models. You don't really have to worry much, like we will cover everything from the basics, but in a sense, most of the times you would not actually have to use some of these advanced functions. So we'll be teaching you a lot of advanced functions in NumPy, and tomorrow we'll also teach you a lot of advanced functions in Pandas. But more often than not, you really don't have to go to those advanced topics. So stay put, right? Let's begin our journey on NumPy and Pandas, and I hope you enjoy these sessions as well. The Cloudbook for NumPy is different than the one you used for Python. So on the YouTube video description, you will find the link to the NumPy Cloudbook. So please go ahead. You have to hit Run Cloudbook button. Enter a new name for the Cloudbook, enter a new password for the Cloudbook. This has to be done the same way as before. You will then be presented with the Cloudbook screen. You have to power on the Cloudbook and open the Cloudbook. It's exactly same as you did at the first weekend when we started with the Python Cloudbook. You have to do the same thing. The Cloudbook for NumPy is different. So please do run your Cloudbooks, and then so that you can follow Suvir along with the coding session during the training. For any reason, if your Cloudbook is not opening, I would just request you to once please log out from your BlobCity Cloud account and log in back again, and it should work after that. And before we begin with the session, a very, very personal thank you to Ganzard11. And Ganzard11 gave us a super chat message for 100 rupees. That's kind of showing support and appreciation for the course. Ganzard, we really, really appreciate your support. And really appreciate doing this training. We're liking this. The trainers have taken a lot of effort in preparing the content, for the program. They're also taking a lot of effort to conduct the sessions for all of you. And our only hope is to make sure you get value. So Ganzard, this is really, really, really valuable feedback. This is kind of telling us that you really appreciate the session and you're liking the course and you're seeing value from it. So thank you so much for that 100 rupee contribution that you've made. For anyone else, if you would like to make a contribution, you can show your appreciation. You can even make small amount contributions. It's just for a show of appreciation for the trainer. It keeps us all motivated. You will see a super chat and super, sticker icon at the bottom of your chat screen on YouTube live chat. Please do go ahead and please do send us a super chat message. It gives us a tremendous feedback that you're really, really appreciating what we're doing. It's not about the money. It's about just letting us know that you really, really are liking the session. So we would love to hear from you if you really like the session. Ganzard11, thank you so much once again for doing that on the last session. So we're over to you, and let's begin this awesome journey on NumPy programming today.
Thank you, Sanket, for that introduction. So I welcome all of you back. Good afternoon. Yes, hello everyone. Welcome back into this session. I haven't shared the screen yet, which I'm going to do that in just a moment. Now, just as an extension, yes, this session is going to be interactive and comprehensive. This session is going to be a little different than what we have done before. So if any questions, please put that onto the chat box. I'll try to answer that. But yes, and since this is post-lunch session, so I'll try to keep it interactive so that none of us lose any kind of a focus from this session. Okay, so NumPy is another extension to Python. Is it an extension to Python for numerical computations? NumPy stands for numerical Python. Now, what kind of data we can support in numerical Python? Well, there are two types of data, right? At a very high level. One is a quantitative and the other one is a qualitative. I'm sure everyone knows about that part. So the qualitative is all about in which district or a region you live, what is the color of your hair, what kind of a fruit you eat, and those kind of things are all qualitative. When it comes to numbers like measures or metrics, those kind of things fall into the number system of Python. And how do you allocate numbers through maybe external data or through the data which we generate through Python? But how do you collect data is through arrays. So as arrays are multidimensional, we're going to look at that, what are dimensions and how they are comprehended in Python very quickly. We'll try to fasten up on this because this is a NumPy session. We'll see how far we're able to absorb this one. So NumPy simply stands for numerical Python. It is a Python library responsible for carrying out complex array operations. Now, so far we have seen list and tuples, right? So you saw that how do we create a list by standing bracket, or how do we create a tuple by using a round bracket? But arrays are more to that. As we had seen that list is actually higher level data structure compared to arrays, which we use in Python. But these arrays are a little different than what is typically used in Python. Okay, how it is that it allows, how it is different. It allows to perform various operations like linear algebra operations, Fourier transformation series operations, or random number or sample generation of the data. It is almost 50 times faster than any generic Python arrays or lists, which were written in C or C++. Now we will do, in order to switch to this functionality, we will use installation of NumPy. So the first thing that we need to do is install NumPy. And we are not going to use a conda part of it. We're going to use a pip part of it. Pip is usually used for Linux systems. Conda you can use when you have installed Anaconda on your system. But yes, here we are on the Jupyter on the Linux part. So pip install NumPy. It will install NumPy for us. So, and if you want to check the version for NumPy, you can simply say NumPy version. I'm going to show you that in just a moment. But let's see, can we really import the library? Do we have the flexibility to do it? Okay, no module name NumPy. So it seems like I will have to install it. So I'm going to use a pip installation type. And in Jupyter till the time this is a star, it is running, and the moment we get the number, that means it has finished. So you need to restart the kernel to use updated packages. And we got the NumPy version 1.2. Okay, so we can go and we can say just a restart. Restart the kernel. Kernel is ready, we can restart. And then let's go and import. So first thing is that we need to import this library for NumPy. And as a common practice, we are using NP as an abbreviation to NumPy. So NP stands for numerical Python NumPy. So we may use any other different name. If you'd like to, instead of NP, you can use any other name. But this is more convenient. And this is actually a standard followed across in the community as well. So you can follow that along. To get started, we'll create a random matrix with NumPy, and we will be using NumPy to mainly handle matrices and perform operations of that. So far, matrix we have seen only in our elementary mathematical books. We have not seen anything other than then. We have seen matrices in Excel, and people, those who are working on some part of business intelligence, so they must have seen of some part of matrices. But that's again like a pivot. It's okay. So that's fine, exactly. So far we saw, if we compare our studies from last weekend, then we have studied list, but again, we have seen only a single dimension. Tuples, we have seen only a single dimension. But let's see, can we create a matrice which is two-dimensional, correct? Matrice is two-dimensional. It has rows and it has columns. So let's see if we can do it. So we can now operate on the variable NP to use NumPy functions to get started, create a random matrix. And not sure if there's a code here, but let's say NP dot underscore version, if I'm able to see, and you can see that I've got a version called as 1.20.3. So you can check the NumPy version specifically, explicitly, if you want to do it by using an np dot version checker. 1.20 is the version. We will go ahead and understand NumPy and what is this matrix. So in several machine learning programs, we have to deal with matrices. Rather, most data we have is in the form of a matrix. So as let's say if you want to compare two different images and you want to check whether these two different images are identical to each other or they have some of the other differences. So you will have to subtract the image, one image subtract with the other image, right? So this is a simple matrix operation. You have taken one two-dimensional image, which is one matrix. You have taken another two-dimensional image, two-dimensional matrix, which is an image, and you would like to do matrix one subtract matrix two, and if the difference is zero, that means both the images are identical. So this is what the NumPy is used for. So for multi-dimensional analysis on the quantitative data. So we can consider, for example, simple sales register. This sales register could come from an Excel, and this data will have the rows and the columns. And the row and the column format is considered as a two-dimensional matrix because it has a two dimensions. One is a row, other is a column. This means that if you have Excel sheet with 5 columns and 100 rows, then you have a matrix of size 100 by 5, or we would still write in NumPy as 100, 5, but still this would be a two-dimensional. Okay, so I'm sure that everyone knows what this kind of text it is coming. Even image data and video data is a form of matrices. We represent images as three-dimensional, where the color is the third dimension and the pixels are in the row and the column format, which is the two-dimension. So we need to keep in mind that numerical Python is not the only option for handling matrix information. We could simply use arrays also, but NumPy is actually designed to handle really large volumes of data. That's what we discussed about video files and the image files. Just imagine if there is a 4K HD video or maybe an image, the minimum size for that is going to be around 8 GB. Sorry, for one image is going to be around 8 megabytes to 10 megabytes. So, and if you have thousands of images, then that's going to pile up to many gigabytes of data, right? So I'm sure that even Excel would not handle more than 100 megabytes of data to open up. So when you want to handle really this large amount of data, you need those kind of library packages, and NumPy is an efficient way to handle that. There are also other parameters which matters, like whether you're using a CPU on the PC or you're using it's like a GPU operated. So when you're dealing with image and then video files, it is always recommended that you use the GPU. So what are simple arrays? Simple arrays are nothing but they are lists, but when those arrays are converted into multi-dimensional, they become either a matrix or they become a NumPy array. Okay, so let's look at creating our first matrice. Before we start creating our array, let's understand what is a matrix. A matrix is a collection of numbers arranged into a fixed number of columns and rows. So you can see this. We have got 3 rows and 3 columns, so it forms a 3 by 3 matrix of 2 dimension. This is a 3 by 3 matrix because it has got 3 rows. Each number that makes up the matrix is called as an element of the matrix. And you can see that this matrix is actually a collection of different arrays. So you can see 104 is one array, negative 1 is one array, 3, 4.6, and 0 is one array. This is vertically, and horizontally, if you see 1, negative 2, 3, 0, 8, 4.6, they are all different arrays. So we've got around 6 different arrays which are being created with an element size of 3. Okay, so let us create a first matrix using the random number generator. And NumPy provides several functions to quickly create matrix. So let's see this one. I'm saying that you create, you get me np.random.randn. Randn stands for give me a sample of random normal distributed numbers. So as you know that we have different types of distributions available to us in statistics in data mining. So we have discrete distributions and also we have continuous distributions, correct? So like so normal distribution is one thing that we always look for. So we are saying that you draw or you give us 9 different random numbers which are drawn randomly from a normal distribution. So that is around, give me that in a shape of 3 by 3. That means you give me a 3 by 3 matrix. And this is a square matrix. Square matrix means which has got both edges like in rows and the columns of equal numbers. So that becomes a square matrix. Let us now try creating a matrix with 2 rows and 3 columns. So you can see the output for a matrix which is 2 rows and 3 columns are likely to be this one. Also, you can quickly try 3 rows and 2 columns, which looks like this. Correct? So that means we have come to know that we can create multi-dimensional data using NumPy. When we want to create multi-dimensional data using NumPy in the form of matrix, then it has to be in a form of arrays, which are multi-dimensional and which forms some form of a matrix. That's what we have seen. But let's see moving forward how we can use this with our custom values rather than using the distribution or normal distribution random samples. We'll try to specify our numbers. Also, we'll try to do some operations. So performing mathematical operations is like we create a data of matrix 2 by 3. So you can see there's a 2 row and 3 columns. Then you've got around another same matrix. I'm multiplying that with number 10, which like makes our negative 0.41 into negative 4.12, and so on and so forth. So every value of that matrix is multiplied with a single scalar value of number 10. Now, is this possible in a list? Guys, I can ask this question from people who have already undergone. Yes, Supreet has a question. Instead of float, if you want the integer matrix, yes, you can very well have that, Supreet. So matrix is actually one thing, couple of things which I want to highlight is the NumPy. So you can see this one. You have to, let's say, for example, this one. Okay, so this is like, I would say this is my underscore array, and I'm going to push some random matrix into my underscore array. And I want to see what is the type of this my underscore array. Okay. So the my underscore array, you can see it did not say that it's a matrix. It said that it's a ND array. It's a NumPy n dimensional array. Okay. We can also go with my underscore array and can check different methods available into my underscore array. You can say that I also want to see the shape of this array. Okay, so I'll go to the S part and you can see there's a shape, and you can see that this also showing that this particular n-dimensional array is actually a 3 by 2. It has got 3 rows and 2 columns. But we were talking about list. So let's say I have list one, which is 1, 2. I'm just keeping it simple. List 2 and 3, 4. Or we don't need list 2 right now. We simply need list 1. Okay, we're going to run this and then say list 1 into 10. You know what's going to happen? It's going to print your 1 and 2 10 different times if you try to do this via list. So when you type in the type of your list 1, it's actually a Python list. Can you see this? It's actually a Python list. But if you want to do quantitative or operations on numbers, it's indeed required for us to change the list into a NumPy ND array, n-dimensional array. So I will have to change this list 1 as an array. And once I change that, as an array, np dot nd array, and I want to say list 1 is an nd array. Okay, so you can see this now. My numbers have whatever values I had, and that has specifically changed into my array. So you have to get your data in the form of arrays in order to get these operations done. Okay, so when you say data into 10, it's going to multiply every element of your matrix with the scalar value 10. This isn't possible in vectors, that is tuples, or it's not possible in lists. So just to keep in mind, the above multiplication will not change the original matrix. It will return a new matrix with values of the previous matrix. If you want, we can load this into another new array or a matrix, which will store the values. So there are several types of functions that we can apply, like mathematical functions that we can perform on these matrices. Let's say some simple ones are data. So this is what our the matrix is, and we want to say data plus data, so it's going to add up 0.4 to 0.8. Add one element to each of the metrics, and this is such a simple operation that we wanted to perform that on vectors and list, but that didn't turn out to be good. So we are using arrays to do this. So data plus 1, that means you add up this number to any element. Shilpi, you can raise that question to the admin. They'll be able to tell you that answer for that one. Simple operations, right? So adding 1 to each of the element of the matrix is going to give us the straightforward answers to that. Divide by half. You must have seen different, the images which we open on our Windows environment. There are some options to change the shape, right? Not shape, sorry. There are some options to change the features of the image, right? Wherein you can make the image on the grayscale, like black and white. You can change the color, you can change the contrast, all these things. So what do you think is happening? In the backend, there are some calculations which are dividing those arrays by certain numbers so that eventually you receive a new array, which is a new little different looking picture than what you had original picture was. Maybe it is a little faded than the original one. Maybe the style has come up a little differently. Any other different changes. So these are like calculations which we do a lot on these kind of data. Add two different matrices. So data is equal to, you can check the number of dimensions of this one by specifying ndim. So your object dot ndim, that means it has got 2 dimensions, and your object dot shape is going to give you the number of elements in that. So 3 into 3 is going to be 9 elements. So it has got 3 elements in the rows. It has got 3 rows, not 3 elements. It has got 3 rows, and it has got 3 columns. So data2 print data2.ndim, data2.shape. You can see data and data2. Okay, so there is a problem in not problem, but that's a compliance you can say that we have. That in data1, you can see the shape of this array is 3 by 3. And the shape of the other array is actually 2 by 3. So that means there is an extra row which is added up in the data object. Does Python will NumPy allow us to do these kind of operations between two matrices of different shapes? When we do this, let's say data plus data2, it starts to give an value error saying operands could not be broadcast together with shapes. Now, this might little be different from other programming language. If we try to demonstrate this same thing in R programming, if people have heard, R will not going to stop you from doing these calculations. So what R is going to do, it will calculate you up to whatever row is available, and then it's going to start repeating the calculation from row number 1 automatically. But in Python, it is a little rigid in this term, so it requires the shapes to be identical. So you cannot actually multiply a two-dimensional image with a three-dimensional. That means you cannot multiply a grayscale image with a colored image. You will have to bring both the images on a similar dimensions. Okay, so let's say data2 is now random and created with a 2x3. So it's a 2x3 matrix. We're saying print data1, print data2, and print data1 plus data2. Still the same. So it's not going to, name data is not defined. So let me just go and run this. I will have to actually run from here. Okay, I have the data with me now. So data plus data is going to give us a new matrice. Data plus 1 is going to give us a new matrice. Divide by half is going to give us a new matrice. You can store this if you want. The original matrix is still the same. So the data or dimensions is 2 and the shape is 2x3. Here also data 2 is there, I guess. And then data plus data 2. This actually got together, so it got added. So please kindly ignore this one because this data has a shape of 2x3 and this is also shape of 2x3. So that's how this got added. But if it is of different shapes, it should give us a different error. Basically, the broadcast operations not allowed for different shape and sizes should be the error. But we are concerned about data2 is equal to, we're giving a different value to data2, bringing it into a 2x3 format. And when we do this, we get the output. So we have data1, data2, and then the plus of data1 plus data2. So -2 minus 0.77 is going to give us -1.32. There are some restrictions. Of course, the two metrics should be of the same size if they are to be added to each other or any operation for that matter. It will not work if you take matrices with different dimensions. So shape and dimensions, both are important. I hope everyone is able to understand what is a shape and dimension. And before we could even, write these things in a NumPy or in a screen like this, what I'm demonstrating, you should analyze this visually, that how a cube looks like. You have seen a cube, could be a Rubik's cube, which is like a three-dimensional, but it has got almost like 6 sides. So the Rubik's cube have 6 sides. It is of 3 dimensions. It can have more than 3 dimensions, but you can only visualize, but you cannot really picture that out. So you can think of NumPy array to be looking like a Rubik's cube, just like this one. Can you see this one? This is where you have the rows and this is where you have the columns. So if you see the blocks, every block is an element. So if you just talk about one side, if you just see one side, then this is actually a 3x3 array. This is again a 3x3. Can you see this? This is the second dimension. This is the third dimension. Dimension is from which angle you're looking at. So if you look your house, from a helicopter, or maybe from a Google map, you can see that you are actually looking your house from a different dimension. Okay, so you can take NumPy arrays just like Rubik's cubes, or you can take a, a bird's eye view of how your house is going to look from the sky, some meters above the ground. So yes, NumPy is that. And it can not just have one cube, it can have multiple cubes, and it can do several different mathematical operations on those cubes. NumPy is really fast. Okay, let's see how fast it is. So the biggest advantage of NumPy is that it is really fast, and that's the whole reason we use it. So let us compare a NumPy array to a Python list. We say that arrays no more exist in Python because of a higher level of library, higher level of data structure called as lists. So Python arrays have been replaced with lists. And lists are also multidimensional. They're also modern type arrays. But so when the list can do the same, multidimensional list can do the same operation if required, like arrays, why do you use arrays? We use arrays because it is much faster. So let's take both the array and the list of same size, and we will perform exactly the same operation on both the items. We will measure the time it takes to run for both, and we will have a comparison. Okay, so let's see. This is a NumPy array because I'm using an np.arange. So just guys, just as a heads up for NumPy, you can, whenever you use np dot anything like np dot once, okay, so you have these, uh, np dot once, let's say 2. I have these array, and so whenever using np dot zeros, I have np dot zeros as a thing which I want to load. Okay, so this is function np dot zeros. I would like to say 0. You can see is a blank array, whatever. If I'm saying np dot nd array, which is like, or np dot nan for that matter, you can see nan is actually not a number. And where do we use, let's say you want to create a list of my list, let's say 1 comma 2 comma np dot nan. You can use a list like this, and when you say print of list 1, you can see there is an NaN over there, count, there's not a number actually which is there, but that's fine. So whenever using an NP, by default, it has to go with a NumPy data type, okay? And when you want to do any operations regarding NumPy, then the object has to be in the NumPy format. So looking at this code, which is given below, np.arange, so that means whatever value I'll check on that, Niranjan, maybe sometime later on that code. Okay. So import NumPy as np dot a range. So I've got around like 100,000 observations I've put into ARR, as an ARR is actually a NumPy array. And there's a list of range, again, around 100,000 observations I have in that. And there is a magic time which I'm using. So ampersand time, I'm using the for loop for underscore in the range of 10, which is like you run this 10 times. Array 2 is equal to array into multiplied by 2. All right. This is for checking the performance of the arrays. So what is happening is I'm multiplying 2 with every element of my array, and it is taking around what, 2.77 milliseconds to do this. What about the list? So you can see there's a time function again for this. Now in the list, as you know, see, this is the advantage here. You can see this is the advantage. You are not using a loop here to do this. You are applying this as an apply entire on the list, entire on the arrays which you have as a whole block of object. Here you don't have my list as an entire block of object. So what you have to do is, in this list, if you want to pick items, you have to pick it one by one, because list would not allow you to multiply it once, because list is actually an iterable object in Python. So for I in the range of my list, you multiply every observation of list with 2 for X in the list. And when you try to run this, the same thing, it takes around 125 milliseconds. Now, since this is a smaller amount of data, so getting the feel of uh, how long it is taking will not be very evident from this small piece of code because we have simply taken handful of observations. But if these observations really stretch up and scale up to millions and millions of records, then definitely you can still think that the NumPy is going to be 100 times much faster. So if your list operation is taking 100 hours, your NumPy is practically going to finish that in just 1 hour. So just imagine, days and days and days of operations, almost like 4 to 5 days of operations just finished in maybe 1 hour. So that fast the NumPy is. Okay, so we can see that we have taken a large array so that the time difference is noticeable, and then the time to perform of the array was really small. And there's many reasons to this because n-dimensional object is directly stored in the memory, so you can directly access the objects from the memory. And secondly, you don't have to iterate on all the elements which we have. It's already all the elements are known to the memory, so the memory locations are known for those elements, and it's just like one one operation and boom, everything, all the elements gets loaded. When handling large data, NumPy based algorithms are generally 100 times faster than pure Python counterparts like lists, and they also use significantly less memory. So when handling large data, the CPU time is not your problem. You might actually run out of RAM. So NumPy is optimized to save RAM, so it can perform same operations faster with a lesser memory footprint. Now you can see, um, now you'll recall why data structures are important. Now, see, we are living in the 21st century, so we have NumPy. As we move on with the time, we mature on particular things. So the computer society is currently using NumPy as the fastest mode of calculations. But as we move forward, we might encounter other data structures which might come up to be more mature than NumPy. But for now, we have NumPy with us, which can really do an outstanding job when it comes to linear algebra calculations. I hope it's the first lesson is quite clear. All right, so let's understand this little further in a little depth. Dimensions and shapes. So first things is like we need to understand, we'll start by creating a list. So you can see that we have a list and it has 1, 2, 3, 4, 5 as an elements. Let's create, an array from this list, which is actually a NumPy array. So you can see that list one is an object. And I'm saying you convert this list one into an np.array into a matrix one. And you can see that we still have this 1, 2, 3, 4, 5 into an nd array object. So what changed? Nothing actually changed. Mat1 is exactly same as list. Well, not a lot has changed. They both appear the same, but when you print them, they are actually completely different objects. You can see that there is a comma separated values in this list one. And in this matrix, you can see that this is considered as a whole. List one is of type list, where mat1 is of type nd array. Nd array is a class within the NumPy package. Okay, so if you want to confirm that, you can simply say print of type of mat1. You can see it is a class of nd array. You can see here print of type of list one. You can see it's going to give us class of list. Anil has a question why we have mentioned ampersand time. That's one of the magic function. If you want anything to be printed in line, those are inline functions, Anil. So let's say if you're running a plotting library, then you don't. So by default, it doesn't give you the output. So you have to specify that, okay, you print this inline. So you wanted to print the time it takes. So that's the reason we have used ampersand time. You can similarly use ampersand system date to print the date also if you want. And you can also use inline keywords. So those are like the smaller basic things. Once we move on, we're going to get the hand on that. Okay, so we got the differences now. So you know that if you really want to behave if you really want to use you want to make the best use of what is given to us in NumPy, we have to first convert the object into a NumPy array. So let us confirm this by looking at the specifications. So either you can use the type which I used earlier, or you can use the list1 question mark or the mat1 question mark. And when you run them, you will see that the list is actually a list and mat1 is actually an ND array. Let's understand what is 1D array. And these notes are really comprehensive, guys. So please do not ignore these notes because they are really elementary notes. Plus, it has an essence of practical approach as well. So please, after the sessions, you can go through these notes very well. Let's understand one dimensionality. So how do we define a one-dimensional array or 1D array? An array is said to be one-dimensional, either the number of columns or rows, either the number of rows or the columns are. So our mat1 is a 1D array because it has just got one row and 5 different columns. So in linear algebra, 1D array is simply called a vector. We might interchangeably use the term vector and 1D array, so get used to it. Now, if you wanted to create a 1D array that has 1 columns and 5 different rows, how do we do that? So let's see it differently in this way. Can you see this? So we are going to do that using a list first and then ND array. So we are saying that you create different lists within list2. These are like 4 in type, right? So this is a list in itself. This is a list in itself. This is a list in itself. And we're saying np.array of list2, and you print that matrix 2. So you can see that the list2 actually created 5 different independent lists. Correct? That's what we said. And in order to create a vertical of one-dimensional, which is a column vector, you can say this one. Actually, this is a column vector. These are all column vectors. We added list with the primary one. So we created a main list, but instead of adding plain numbers, we created different list for that. You know why? Because lists are multidimensional. It can just not store list in one type, but it can store different lists in itself. A list can have a sublists also. So you can also create lists like, you have this one, you can have a comma in that, and you can have 9, 0, 6. You can have further list as a sublist, since lists are multidimensional. So that's what we did, is like we created individual lists and we converted them into arrays. And what happened is we got a one-dimensional array with 4 rows and 1 column. So let us spend some more time to understand the data type for each of the item here. So list2, now what do you think that the data type for list2 is going to be now? Of course, an ND array. Okay, a list2, okay, list2 not found. I haven't run this code, so let me run this one. And let's see what is the type of list2 now. List2 is a type of list. Just give me 1 second. Okay, it's mat2 actually, my apologies. List2 is going to be a type of list, and the mat2 is going to be a type of ND array. So we know list2 is definitely a type of list. What about the element within the list? So, okay, no problem. So we will going to insert another cell here. I'm going to say you give me the items for list2. These are the items for list2. And what do you think is going to happen if I say list2 and item 0? It's going to give us this one or the entire 1, 2, 3. Okay, let's see that. So I'm going to insert this. It's going to say a list of length only 1. And I should be printing this one, print of list2 item 1. see that it is a type of list, but we simply got one item in that. You can say one vector or one element of that we have got it. So isn't the first element of list 2, which is also a list. So just to be sure, how does this compare to the item list 1? So you can say list 1 has got item 0. Same things, there's nothing different in this. Okay, so we have list 2, which is a list. And let's say item number 1 for list 1 is actually an integer. I hope that's clear. Let me type in list 2 also. There's a bit of a confusion. So I have a list 1. You can see this is list 1. And this is list 2. And I'm saying that you get me the first element of list 1, this one, which is an integer. I'm saying in this part, you get me the first element of list 2, this one, which is actually a list. So this concludes one-dimensional array. So all lists, as you just saw, are all one-dimensional arrays. Now let's go ahead and create two-dimensional lists or two-dimensional arrays. In the same thing, the way we created one element in each of the list arrays, now we're going to extend those elements by one more column. So let's say instead of 1, 2, 3, 4, we are saying 1 and 1, 2 and 2, which you can see it on the screen very well. And now you can say this is a single list. This is a single list. So we got 4 lists inside the list. Okay. 4 sublists inside a list we have. So Mat 2D, again, we're going to convert this into a different matrix or an array form. And when we run this, we can see now we can start creating matrices now. Now this matrix is of shape 4 by 2 because it has got maybe 4 rows and 2 columns. These notes are very well available in the logins, guys. So for Sunil and Abhijit, for anyone else, you can access them very well. If it asks for the login password, then you must have specified the password sometime in the past. So no difference. I'm sure that I am leaving no room for confusions. It is very straightforward. So when we created a two-dimensional list, and then we converted that into an ND array. So as a result, we effectively got an array that has got 4 rows and 2 columns. Very straightforward and simple. So keep in mind, each row is actually an independent list. This one and 2 and 2 and 3 and 3 and 4 is actually an independent list. There's a 1, 4 missing here actually. Why use two-dimensional arrays? It is simple actually. Most of the data sets you will use will be in 2D form. If you have data in Excel, you want to read Excel data. The same, it will be in 2D. You can easily represent any tabular data. Most structured data will be in 2D form. So here are some of the example data sets. Let's look at this one, Titanic data set or Auto MPG data set. These are all available inside Python. Credit card fraud detection data set. We can represent all of these data sets as 2D matrices. Let's talk about three-dimensional arrays. So an array that has 2 dimensions as its elements is called a three-dimensional. 2 arrays as its elements is called a three-dimensional. That is correct. So you can see this one. This one is a 2D list. Oh, very well, correct. So if I run this, It's just going to create two-dimensional things. What about three-dimensional? This is, what do you think? This one is going to create a three-dimensional? Yes. Okay, let's understand this one. So the process to create a three-dimensional is same as that of creating a 2D array. So let's look at an example. So list of 2D is, this is one list for me, okay? And this is another list for me, the list 2. And when I'm creating a third list, I'm creating like a one list out of list 2D1 and list 2D2. And once I have this structure, I'm converting that into an ND array. In my previous classes, I've been giving us one remarks on these dimensions to understand the simplicity of these dimensions. If you want to understand that whether this is a 2D or a 3D or a 1D array or object, the simple thing is to count the number of brackets available to the object. So you can see the moment until this was a 2D list, you can see there are two brackets to this at the start. I mean, you can include the ones which forms a vector or maybe a list itself. You can include these ones. You can see there are two brackets, which means there are two-dimensional data. When you create a single-dimensional list, you create a single bracket, right? You say my list is equal to standing bracket 1, 2. This is again a list. So when this is a list, can you see what is the dimension to the list, to this list? It is a single dimension because it has got a single bracket. This is a 2-dimension because it has got two brackets. And this becomes a 3-dimension because it has now got 3 brackets in this. So the shape of this, so what possibly going to be the shape of this? So instead earlier where we used to get the shape, so how do you convert this into? So I'm going to say print, np dot nd array of my list. I'm converting this into my list as a an nd array, and then I'm going to say that you get me the shape for this. Can you see it is getting a shape? It's not actually a shape, it's just a tuple. So it's just giving you 1, 2. I will have to put this into as into an array. So I say my array is equal to np dot nd array of my list. And I'm going to say print type of, because I'm going to check my array, print type of my array. You can see it's a class of NumPy. Now we can say my array, which I've written, which is actually an ND array. I would say give me the shape for that. It's saying it's 1 by 2. So here also it's 1 by 2, and here also it's 1 by 2. So what does this mean? It has got 1 row and 2 columns. So whenever we get 1 row, that means it's just a 1 dimension over there, right? So here also, when you check the shape, which you're going to do that very soon later in the bottom section. But when you see the shape, there's going to be an extra dimension which will add it to a 1, 2, something is going to be there. Let's understand this. So I hope this part of three-dimensional part is clear. Anything that I would like to explain from this is that if you want to slice this, so mat 3D standing bracket 0, you can see that it has just got the first part for us. So I've just used 0. So this means you slice first block of array or first element of that array, and the first element is nothing but this two-dimensional. This is two-dimensional matrix which we have it out here. Let's see this one. So again, can you see this is a 3-dimensional because the number of brackets are 3. First, then second, and then this is a list, and then the lists. You can see this is actually one list. There's actually one list. It is a list within a list. This is also a list within a list, and then this is one list. Can you see this as a whole is one list, and then nested lists within it. So there's a good question. When we say it is a row vector or a column vector, see, vector has got only direction and a magnitude. A vector will never have a dimension. So when you say row or a column, you're actually wanting to specify an axis to that. But vectors, they lack access. They don't have access at all, AXIS. So you don't specify 0 as rows or 1 as columns. They don't have access, so they don't have a dimension. So always vectors are, they only have a direction and a magnitude. Okay, so you cannot say it's a row vector or a column vector. It's just a vector. I hope things are clear, and I hope you are also able to understand what's the three-dimensionality in this part. And I gave you a simple trick to know, how many dimension an object is. Just simply count the number of brackets. Why use 3D arrays? There is a lot of content that comes in a 3D format, which has got rows and the columns. And for each of that 2D matrix, there is some property associated up in the third dimension for that. So as an example, use a case of 3D image. An image consists of two-dimensional pixels, right? We've got rows and the columns, and we've got pixels in that. And each pixel has a red, green, blue value, which is RGB values. So the RGB stands for the colors. Combinations of RGB colors that make the effective color are basically the pixel colors. So let's take a look at an image, this one. So an image is simply a matrix of pixels. Check this one out. Can you see now? The only thing that I did not show you, which I wanted to, is we did not see, the add 3D dot shape. Can you see? This is different than what shape we've been seeing up here in the top. Can you see this? If you want to see the shape for this, we will have to convert that into, that's fine. But for this one, it will have a two-dimensional. And for 3D, we are already getting the shape, which is 2, 2, 3. What does this mean? What does this 2, 2, 3 means? 2, 2, 3 means that you have two matrix of 2 by 3 each, of size 2 by 3 each. So the first comes the number of matrices, and then the second comes the shape of those matrices. And you cannot have different shapes in this part. So we have combined two different two-dimensional arrays to make a three-dimensional array. All lists must be appropriately sized to make a full-form 3D matrix. Why we are using three-dimensional arrays? There's a lot of content. So let's go back to that image and see about this one. You can now say it has a shape of what, 500 by 800 by 3. Actually, it should have been 3, 500 by 800, but that's fine. We'll move further and investigate. So this is where the shape is going to be. Okay, great. So 500 is the width of the image, 800 is the height of the image, and 3 is the color channel of the image. So color channel is all channels we have, like red, green, blue, but just picking that as a dimension. Okay, so for each image, and there's a channel associated to that, which will give information about the color of the image. Therefore, images are three-dimensional in matrix. Here's a small text on how RGB color codes work. So what I'm going to do, guys, I'm going to we're going to skim through this because this will not uh, give a lot of stress on NumPy. It's just on how RGB color works for images. So you can have a read on this, and I'm sure for people who were in engineering, they already know this a bit. For people who are not, they can read this block. It's all about what are the values. Like generally default, we have 255. And when we change the values to some different values like 00, how does the colors basically go absent? So in this, the colors are really absent. What these numbers mean that they have some specific color, let's say white. If you have 255, so we have some colors like black, whatever the pixel value for that is going to be. So there are a couple of things like 255, 0 and 0, which will make a red color. This will make a green color. This will make a blue color. This would make a dark red color, whatever numbers we have. And you can look up the RGB values from any cheat sheet, which we may find on Google, and you can do that. If you want to convert any image to a grayscale, then you will have to suppress the RGB dimension over there by making it, all zeros. So grayscale images are actually a two-dimensional because you are making the RGB layer as to be completely zero over there. So there is only two-dimensionality to the objects. And so some theoretical text. So in a one-dimensional matrix, the the shape should look like this, 6 comma. So in one dimension, we just have 6 comma and nothing after that, because there's no column in a vector or in one dimension. It denotes that the matrix is one dimensional and there are 6 rows in this. In the second one, that is a 2 comma 2 comma 3, denote that there are 2 matrices of 2 by 3 each matrix of shape 2 by 3 each of the matrix, 2 comma 2 comma 3. So 2 matrix of 2 by 3. What if you have more than 3 dimensions? So as the level of complexity increases, the dimensions keep increasing algebraically. So we call it as n dimensions. Just to give an example for this one, as everyone has been saying that please support with an example. So what are the example I can come up with is, in a principal component analysis, when you do the rotations, I'm not sure how many people have studied SPSS or any equivalent tool for that matter. So PCA is like reducing the dimensions in your data. So there is a technique called as rotation. Okay, when you rotate the data, it gives you a different angle of the columns which you're likely to pick for the reliability of the model. Okay, so when you pick up a data for study, you have to first find out the reliability for that. Because if you just pick up the numbers and start doing your research after 6 months of hard work, you will come to know this data is absolutely worthless. So you have to first do the reliability check and then go on with other processes like dimensionality reductions. So there is a rotation factor, okay, that is again based on dimensions. That is one of the examples that I could give you. So to make it a 4-dimensional array, we would simply put 3D arrays into a list and so on and so forth to make any number of dimensions. But the only thing is practically plotting. Plot also you can do, but kind of creating a virtual picture of that, only a computer can literally place those objects for you in more than 3 dimensions. So let's go ahead and determine the shape and dimensions for this one. So we have already seen this to a part. So if you have a list and then you have converted that list into a 2D matrix, and if you want to see the shape and the size, you can simply, if you want to see the shape and the dimensions, you can simply run the shape and ending methods. We can say that this is of shape, this matrix is of shape 4 by 2 with 4 rows and 2 columns, and it has got 2 dimensions. Let's see this one. So matrix, you can see that how many columns, the brackets it has got only 1 bracket. How many bracket this guy had, you can see first and the second, 2 brackets. So that's the reason it had got 2 dimensions here. If you simply prepare a list with a single bracket, here you can see, and when you get the shape and the ending for that, you can see that there's only one dimension to this. Shape is also, you can see, only 4. It has got an absent. The second dimension is absent over there. It's like creating a roof for your home. You know, you've just built the walls. So this shape is like you have just built the walls, but you forgot to mention the ceiling or the roof of the house. If you bring in the roof of the house, that will complete 2 dimensionalities. And if you start bringing in items inside the house, that may convert up to a 3-dimensional matrix. So, Manoj, how the rotation works using NumPy? No, Alok, it was just a reference example. There is no rotation in NumPy. But I was saying that I was looking at the data from different perspectives. Initially, you were looking the data, let's say for top 5 customers. Okay, this is your point of view that you want to look your customers. You want to see your top 5 customers for profit, let's say. Okay, to give a basic example on this one, because dimensionality is not just restricted to data science, but it is also to business analytics. So when you're saying that you give me data for top 5 customers, this is one dimension. Okay, this is like you're looking at from one dimension. If you say that you give me top 5 customers for each region, okay, and now you can see this is a different dimension that you added region into perspective. And if you say that you give me customers for top 5 regions for top 5 countries, and then you've added up a third dimension on that, that is countries. So this is how you segregate or segment the data. Alok, you can refer that rotation part. So the rotation does exactly what I just gave an example for the PI part. Manoj has a question, np.array and np.nd array. So I can very well tell you that, Manoj, array is basically for one-dimensional list you have, you can convert that into an array. But if you want to convert ND array, you have to define the shape or size. So you can check out the arguments for these two things. You can just put a question mark and run it, and you will see the different arguments that it requires. So very interesting, right? These dimensionalities. So for people, those who are new, I'm sure it must be exciting, and because it's really hard to imagine things like this, but yes, NumPy is doing that for us. So we confirm that this is a one-dimensional matrix. So let's say this one 1 and 2, it is 2-dimensional. Print matrix 2, give me the shape. Shape is actually 4 by 1. This shape is going to be 4 by 1, and dimension is going to be 2. See, the shape is going to be 4 by 1, and the dimension is going to be 2 because it has got rows and columns. So that is a dimension. So let's try this out with the 3D matrix. So see, number of columns is 3. So this is going to be, so the end dimension is going to be 3. And the shape for this is going to be, what do you suggest the shape for this is going to be? 2 by 2. So the shape for this is actually 2 by 2. Actually, it's 2 matrices of 2 by 1. Okay, you can see this 1 and 2 and 1 and 2. 3 dimensions. 2 by 1. So you can see 2 by 1. So the shape is 2 by 1. So you've got 2 rows and 1 column, and both the matrices are just the same, 2 rows and 1 column. So it has got 2 matrices of shape 2 by 1, and the number of dimensions are 3. Pretty simple, right? So let's say for this one, again, 3 dimensions. And what is going to be the shape? The shape is going to be, like say, 2 matrix of 2 by 2. So 2, 2, 2, 2, 2, 2, and it's 3 dimension. Very straightforward and fun to work with, right, guys? Once we get the knack of this, it actually becomes fun to work. You would want to try that out with different dimensions, not just with different dimensions, you would want to do some operations on that. Probably you can import an image and you can look at the dimensions for a smaller image if you have any size of 10 kilobytes or 20 kilobytes. You can import an image and see the dimensions to that. Try to suppress or enable some dimensions and see what is the output of those images. The images might get little, skewed, or it might get little stretched up if you change the pixels. If you suppress the color, then it might just come up to a grayscale. And that is what happens in any of your operating system photo tools which you have. When you try to make some changes into grayscale or flip the image or something like that, um, all these things which actually happens. The only thing is they are proprietary tools. They have closed source all these things, and they have created an intuitive user interface on top of it. So we're going to learn about basic operations now. So far we have covered about dimensionalities in NumPy, and we have understood the basic structure of NumPy, and we have also understood that why it is important for an object to be in a NumPy format before you analyze any kind of shapes or dimensions or operations on that. So let's see, how do you create arrays, n-dimensional arrays, and how do we do operations on that? You can see this now. Answer to the one which was asked in the question, that what is the difference between an ND array and an NP array. So let's see this one. So we are passing a list and converting that into an array, and you can see that we simply used np.array. That is correct. That is correct, Alok. Can you refer np.rot for what reason it is doing for rot 19? That is for rotation 90. That could be a rotation 90 if you have used Alok. So that could be a part of rotation. You can see that. So you can see that array is successfully created for us. And then we can very well check the type of this array. You can see it is a class of n-dimensional array, so which is good for us moving forward. Let's create an np.arange. So by default, this is going to result in an array because we have used np as a library package to do so. Print of a, which is 0, 1, 2, 3, 4. And you can see that it's just one big chunk of array. Unlike a list, type of a is nd array. np.arange print a type a, and it's again a type of nd array. You can use np.zeros. So you can say you give me 5 different zeros. Again, the type is nd array. Why do you use zeros and all those things? There's a direct method given for zero. So this is useful for quantum computing, not even for not for quantum computing, but if in some matrix operations you need to multiply your arrays with scalar matrices or square matrices for equal proportions. So that time you will use zeros and ones for that. Here, there was a question that we can get a matrix with an integer values. Definitely, we can say you create an np.zeros matrix with the data type as integer 32. You can keep integer 16 also. That will help you preserve memory space. So this way you can say print of a. So this is actually a one-dimensional array. So this is a list there you can refer. So array converts input data like list, tuples, or any sequence type into an ND array. You can explicitly specify the D type. As array convert input to ND array, but do not copy if the input is already an ND array. So a couple of things you can see, most of the things. So we have a range, ones, which we saw zeros, create empty arrays by allocating new memory, but do not populate any values like 1 and 0. So this is like creating an empty ND array, the way we create standing brackets for empty list or dictionaries. Similarly, we can create np.empty. Full is produce an array of the given shape and D type with all values set to the indicated fill value. Okay, we're going to look at all these things. So let's say you have fill NA kind of a structure with you, wherein if your values are NA, you can fill NA with some values. Those things are there. Identity matrix, which is like a square matrix. With the data types, can we create a data type of string? Yes, we can do that. So we can very well create a matrix or an ND array with a string data also, with a Unicode, with floats, complex numbers. Complex numbers can also form matrices or arrays. Integers, we can always create. So arrays are multidimensional, but arrays, are they homogeneous? Correct. So you can say that arrays are homogeneous. That means they only support data of the same type in the array. They cannot tolerate data of different types. So you cannot store complex or string data together. So you can create a matrix or array which is any one of these forms. So if you have 10 by 10 or 10 by 100 kind of a matrix, it should either have all integer values or all float or all complex. Let's see these ones. np.array, it's an array of 1, 2, 3 string elements. And when you say print type of A, it says that we can handle string or any other type in NumPy. So definitely we can say that we can handle. And we are saying a.as type, you change the type for that to integer 32. And when you say this, you can see it is a class of NumPy in 32. We have changed the, you can see the earlier format was like a string in the quotes. Later on, we changed it to an integer value of that type, and you saw that we use int32. So we simply got a NumPy with int32 as a value. You could have simply write the type of B also, not necessary that we need 0. That's going to give us, you can see actually, so I'm going to say Control C, put it here, Control V. You can see now it's an ND array. When I said 0, that time is going to actually pull one of the elements for that. So when we change the type to integer 32, it's actually pulling value 1 and then giving us the type for that. Yes, very well. Alok has a question. Can we perform logical and or operations? Yes, very well, Alok. We will going to do that. These are the operations notebooks, so very well we're going to do that. I hope this code is clear. As type, you can see we converted that. So we're going to do arithmetic operations. So let's say np.array, we've got a 2 by 2 array over here. Here also we got 2 by 2. And when we try to get the output, we can see that we've got this one array here, array B. Can we do A plus B? And the result is going to be this is all ones. So A is all ones. You can see that we've got all. We actually will have to use print of A. Okay, so you can see that we got around 1 for print of A, and then we've got a B. And when we do A plus B, very seamlessly, we get another array which has elements added, though the shape of the object is still the same, that is 2 by 3. So the shape is still the same. That is 2 by 2. Subtraction also the same, the shape is still going to be the same. The only difference is going to difference out the elements. Multiplication, yes, still the same. Division, yes, still the same. Let's look at raising powers. Also, we can raise powers of array values. I'm saying np.power array a values raised to the power of 2. And we actually want to see what is an array a. Array A is a matrix of 2 by 2. We are saying that you raise that with the power of 2, and eventually the result is going to be the same, no difference in values of 1. So let's try the same thing with the B matrix and see if the power raise works. You can see this one. Since we had two values, elements, element value was 2 in matrix B, and when we raised it to another 2, it made it to 4. Okay, now the important point is coming up for reshaping of matrices. This is useful when you're dealing with machine learning libraries like skitlearn or scipy, because these libraries require your input in a certain format. So let's say for skitlearn, you always require your feature variables to be defined, or your training data rather, to be defined in a 2 by 2 format. Not 2 by 2, but it is defined in a dimension of 2. That means your the dimensions, the end dim for your object should be 2. It should have rows and columns. You cannot have one-dimensional input. So that's why sometimes it's important to reshape the data as per the flexibility to accommodate your data. All right, so we can also reshape our matrix using the reshape function. So by shape, we are able to get the shape which it has, the current shape which it has. Could be 3 by 2, could be 3 by 6, anything for that matter. So here we can see this NP is of shape 1 dimension, correct? Can we reshape this? So 1, 2, 3 is just 3 elements. We cannot, it's a odd number of elements, so we cannot break that into a 2 by 2 or a 4 by 4, because if you want 2 by 2, then you should have 2 rows and 2 columns. But it seems that here we just have 3 elements and not 4. So what is the dimension that you can expect? The only dimension we can expect is 1 dimension, 1, 2, 3. If you want to reshape it, how will you reshape this? I'm saying np.reshape. What you want to reshape? I want to reshape A, which is currently 1 dimension, into a 3 by 1. So that means you should have 1, 2, 3 given as, you can see the shape for this, and the dimension is going to still be the same. But let's print the shape. You can see that it has a shape of 3 by 1. That means all the 1, 2, 3 is now appearing as rows, and there's a single column which addresses 1, 2, 3. Shape is again 2. Now we have changed the shape from 1 dimension to a 2 dimension. Reshaping a matrix from shape 1, 8 to 8, 1. Okay, so you can see these are 8 elements. And I'm going to say, you give me the shape for A and you give me the dimensions for the A. Can you see the shape is 8, and there's nothing in the column. So that means obviously it is a 1 dimension object. You reshape this to 8, 1. Now 8, 1 means that you get all the 8 things into the rows and then you place them into 1 column. So you can see that this is 2 dimension now, and the shape is 8, 1. As simple as reshaping 2 dimensions compared to 1 dimensions. Let's say we create a matrix called as 2 by 3. So this is a 2 by 3 matrix. And I would like to, now this is a 2 by 3, correct? So we got even number of elements in these matrices. So we got 2 by 3 means 2 into 3 is 6 elements. And now I can break that 6 into how many different ways? I can either do 2 by 3 or I can do 3 by 2. I can also do 6 by 1, correct? But that's going to be a 2-dimensional, and that's what we're looking for. You can see 2 by 3 is now converted into 3 by 2. There are other ways also. Let's say what happens is you are saying always start your row with, you can start your row like this also. You can say 1, 2, 3 in the columns and 4, 5, 6 in another column. instead of you placing it like this, 2, 1 by 3, 1 by 2, and 3 by 4, and 5 by 6, you can place it as, in the rows 1, 2, 3, and 4, 5, 6. There are methods available inside this. So when you do the, not in the reshape, but yes, in the array part, you have different methods available that you can choose that you would want to give it by a column, or you would want to give it by a row. Can you see this? The order here. So the order is like C is like by columns. So here you can see order is CFA. So wherein C means to read write elements using C like index order. So, you can use these ways to shape the data the way you want. Let's go with another example quickly. Reshaping a matrix from shape 3 by 5 to, so this is again 15, and 5 by 3 is also 15. So that's great. So we can use this. So you can see this is 3 by 5, 15 elements in this matrix. And then I would like to reshape this to another matrix called as C with a 5 by 3 structure. And again, you will see it is 56, 76, 31, and then 44. If you want, you can make it 5, means like entire up till 55 into the rows, and then rest one onto the columns. Let's go with reshaping a 3D matrix. Okay, so when you reshape a 2D matrix, it is required to pass 2 arguments to this, right? So 5, 3 is actually 2 arguments. So I'm sure that in 3D matrix, you will add up another comma and try to redefine the shape to it. Let's go ahead and do it. So this is a 3-dimensional. You can see how many column standing brackets we have. 3. It's a 3-dimension. Let's reshape this. I'm saying that you give me 3 different 2 by 2 matrix out of this. And if you multiply this, 3 into 2 is 6. 6 into 2 is 12. And is this true for this one? 2 2s are 4, and 4 into 3 is 12. 3 into 2 is 6. 6 into 2 is 12. And these are 2 rows of 6 elements each. So 6 and 6 is 12. So we know that our shape is perfect in calculations. So I'm saying that you give me 3 matrix with 2 by 2 shape each. You can divide a particular image into 3 different sections. You can break those images into 3 different parts. You must have seen in some of the web pages, you have the broken images defined on the web page. That is like from an original image, we broke the third part of that, and we just gave that some aesthetic on top of that. So you can break images into parts. Reshaping a matrix from shape 1, 2, 3 to 1, 3, 2. So is the multiplication elements coming to the same? 1 into 2 is 2, and 2 into 3 is 6. 1 into 3 is 3, and 3 into 2 is 6. So yes, we can do it. So this is the original 3D matrix, and we would say you change the shape. You give me 1 matrix with 3 by 2 as the shape. Exactly. Exactly. So Lakshman has reshape looks like a transpose of a matrix and can be reshape part of 2D array. Yes, actually we did that already, Lakshman. So yes, it's more or less like a transpose. Okay, joining of the matrices. So out of the different join functions available, so we can concatenate. So in actually NumPy, axis 1 refers to the rows, and axis 0 refers to the columns. In tomorrow's session, there might be a little confusion, which shouldn't be there, because if you are studying pandas in any of the session, then there's a bit difference in pandas. Pandas rows is actually zeros and columns is 1. In in NumPy, the rows are actually 1 and the columns are 0 in terms of axis. So why this is required when we want to concatenate or join more or 2 arrays together? that is where we need the joining function. So let's see how it operates. I'm going to say my NumPy is already installed. No, my NumPy is not installed in this because it doesn't install for across the workbooks. So I will have to reinstall it. Okay, so it says that it's already satisfied, so no problem. I'll go import NumPy as NP. The first array is a one dimension, and the second one is also a one-dimensional array. And I'm going to say np.concatenate. You can see that we have a very large array now. So the two single arrays were concatenated with a simple operation called as np.concatenate. Let's join two-dimensional arrays. So when now we are joining two-dimensional arrays, it is also important to specify on what dimension we are joining, whether we're joining on the rows or we're joining on the columns of the data set. So let's say our first array is A and our second array is B. The first one is 2 by 3 and the second one is 5 by 3. Now you'll see that it is very easy to append a matrix B to A or A to B, whichever it is, because it actually comes in the same number of columns. But if you try to kind of append or join them together by the help of the rows, let's see what happens. So np.concatenate A comma B access is equal to 0. That means you use the columns. Okay, so you use the columns to concatenate 1, 2, 3, 4, 5, 6, 56, 76, and 31. So let's see what happens. Very straightforward. So we have used 0. That means we want to append the columns. And we saw that the row got added or row got extended a bit to this. Basically, columns received the additional values. Let's try performing this on the axis. Let's see what happens. np.array 1, 2, 3, and this is again some. You can see that now trying to concat on one again with same number of elements on axis 1. Now see, this is going by that because we had to get the same number of elements to concatenate. So np.concatenate A comma B axis is 1. So this is 1, 2, 3. You can see, and 4, 5, 6. It got extended by the rows because axis 1 in NumPy means rows. Concatenation by rows. If it would have been a column, it would have been this value would have been under here. And if the shapes are different, we cannot concatenate that. So joining a 3D array. So we got 3-dimensional in the first one and 3-dimensional. In fact, this is the complete 3-dimensional array A. This is another array, which is again a 3-dimension of shape 2, 1, 3. So you will see the shape is identical. The shape is not identical for these arrays. Let's see how it works. So np.concatenate A and B, and you concatenate that on axis. So if you're concatenating that on axis, it's not going to give us any errors because you see 1, 2, 3 is 3 number of columns here. 7, 8, 9 is again the column. But what about the rows? 1 and 4, 2 rows we have. 7 and 10, 2 rows we have. 99 and 88, 2 rows we have. Okay, so let's go ahead and run this one. Can you see 99, 199, 299 is actually got append to the first block, and the second one got append to the second block, resulting into a new shape of 2 matrices of 3 by 3 each, which is here. You can see how interesting it is, right? So moving forward, Splitting. So joining, we saw how we can join it. So there are two options to join the arrays. I always ensure that the shape of the array is the same. There are two ways. One is the rows and one is the columns. So axis 1 is going to be the rows and axis 0 is going to be the columns for you. We use array split to split the array into n number of parts. So let's say this is a one-dimensional array and I'm saying np.array split a comma 2. So you split that into two different arrays. So my new array is going to be 1, 2, 3 and 4, 5, 6. Again, you will have to keep in mind the elements multiplicity in this part before you define the split. If you define 3, it's going to be 1, 2, 3, 4, 5, 6. If you define 4, not sure what's going to happen when you define 4. Yes, obviously. Roshali has a question. Matrix multiplication, is it possible? Yes, that's what we did some time back also. We added two matrix, right? So 2 by 2 and 2 by 2, A plus B, we added two matrix to get another matrix. We have already done that, Roshali, in the start of this notebook. So let's see what happens, okay, if we define the uneven. So what happens if I define 3? It's going to give us 3 different arrays. What if I define 4? Oh, it's going to give us 4 different arrays. This is also good. It did not give us an error. It said 1, 2 is one array, 3, 4 is second array, fifth one is a third array, sixth one is a fourth array. What happens if we define the fifth one? You can see that it is all going and reducing. What happens if I provide a seventh one? Okay, we have a 7, 1 also, 4, 5, 6, and there's a blank. Can you see there's a blank one? Can we see 10? So do we get those many blank arrays? So this is a good thing that you can wait maybe for the data to come the next time you move on this part. But for now, let's say I want 2 different arrays. The NumPy.random, we used sometime back the rand_n function, which is you draw the random numbers for us from the n normal distribution. So NumPy.random module is responsible for generating arrays with random numbers. Each time you run the below cells, different numbers are generated. So rand_n we saw, and rand_n is actually forming a normal distribution. So we can say this one, import NumPy as np, np.random.rand_n, you give us a 3 by 2. And when we have used np, that means the output is always going to be in an array format. And we have defined the shape here that you give us 3 rows, 2 columns, and the distribution values for that should be drawn from normal distribution. There was a question, can we bring in the integers? Yes, we can bring in the integers. So we can definitely say random.randint. You give me values from 1 to 10, random values from 1 to 10. Give me a size of 3 by 2. That means it should be 3 rows, 2 columns. So you can see that when I run this, and every time you run, since it is a random, the values will keep changing for you. The matrix will keep changing for you. You can lock it by using, different methods. What happens in the so np.random.rand_n is something what we have seen. np.random.randint, that's what we have seen. This is another one. The rand generates an array of float numbers whose shape is to be given from a uniform distribution. So we have normal distribution, non-normal distribution, uniform distribution, which is discrete distribution, many different. We have almost 15 types of distributions. So np.random.rand, which is going to give us float numbers from uniform distribution, and the numbers are going to be this way in the shape of 2 by 4. Now, why these numbers are important to generate? It's actually very, very important. Maybe I may not be able to give you a very relevant part of why it is important right now in data science, but random number generations is very important to test your data, very important to basically be confident on your data. You can create multiple test data sets using random numbers, and you can run different test scenarios on your models, machine learning models, which will give you a higher level of confidence that how accurate your model is going to perform in real scenario. So random numbers are very important. np.random.seed. Now this is something which is new. And what is this? So the seed is associated with the number when the computation is done. Okay, so I will not read this, but in short, I'm going to tell you that seed is useful when you want to lock the randomization over there, because it may happen that you created your model, you created some test data, and you still need to fine tune your model further, which you are planning to do it maybe the next day. You close your workspace and you go off to sleep. You wake up the next morning, you will see that all the numbers have changed because you rerun the script. When you rerun the script, all the random numbers again got shuffled, and you have a new perspective to your model now. But sometimes you would want to lock your observations. So you can use a seed kind of a technique, which is very common across programming languages. So np.random.seed, you give it a unique number, like a key or something, the way we had a key for the dictionary. You can give any number um, between 101 and 100,000 or maybe more, any number which will become the key. And then when you use that number with that key every time, you will see that as many as times you run your random code, your values won't change, because this code is supported with the seed of 5. If you want the person a similar, your colleague, um, if you want to pass on this data set who is working in the same repository as yours, you can tell him or her that you use the seed of 5, which is going to give you my test data, which I used for my um, analysis or training, basically. So it's pretty handy. Um, there's one more important aspect to random numbers. It is called as replacement. So we have a replacement as in the samples. Well, when you draw samples, let's say from item 1 to 10, okay, and you say that I want 20 observations between the range of 1 to 10. So what do you expect the replacement going to be do? Replacement means you get the random numbers with replacement, yes or no. So replacement yes means that you would want the sample to draw the same number which was drawn before also. So if you say you give me 10 or let's say 20 random numbers from a range of 1 to 100, and if you say replacement is true, so there is a likely possibility that the same number will be drawn again from the lot randomly with replacement, means there is going to be a repeat in your randoms. But if you say with no replacement, then all the 20 sample elements which you drew from 1 to 100 range, all the elements are going to be unique. So there is one more part associated with the sampling. So please make a note of that, and you can also refer, that why do we use seed, and then where can we use the sampling technique, which I told you about replacement. Let's look at another example, a very useful part in NumPy that's called as broadcasting. Now, this is one of the important parts. So broadcasting describes how NumPy treats arrays with different shapes of arithmetic operations. So as we saw that when we are dealing with different shapes, multiplication, addition, it's not going to accept. Can we broadcast our arrays, like an extend our arrays, so that when the operation is happening, the operation has the adequate number of elements which it needs to further perform the calculations. So let's say this one, np.array, and I have a b is equal to 2, and we're going to say a into b. So what happened here is the b automatically got broadcasted. So from the above result, we can infer that b is a scalar that stretched during the arithmetic operations into an array with the same shape. So you can see that 1, 2, 3 is actually a single dimension array. B was a scalar, but because of this multiplicative operation, or any operation for that matter, it got extended to two more blocks by copying or being the identical shape of the operand. And both operands uh, got multiplied with an operator multiplication, and the final result is produced. Now this is called as broadcasting or broadcast. So the multiplication of the matrix by the number, not a valid arithmetic operation. That's why the NumPy created an array to stretch itself. So the broadcasting rule. So the size of the axis of both arrays in an operation must either be the same size or one of them must be one. One of them must be one means of size one, basically. Yes, there are constraints, Lakshman. That's what we have seen before. There are constraints for accesses. We'll see that further. Let's go. So let's consider an example. Suppose there's a matrix A and you would like to scale first row by 3 times, second row by 4 times, and third row by 5 times. So you can see this one is of shape 3 by 3. Now, in order to scale the matrix A by given values, we'll make another matrix B. You can see 3, 4, 5. Shape of B is actually 3 rows and 1 column. I hope you're getting it. Let's see this. Okay, so this is like shape of 3 by 3. So we've got 3 rows and 3 columns. And this is a shape of 3 by 1. That means we simply have got 3 rows, but we don't have 3 columns. We just have 1 column. So as the broadcasting rule says, size of both the arrays are the same. That is, size of A is 3 and the size of B is also 3. One of the arrays axis is equal to 1 and an axis of array B is equal to 1. So you can see that is y-axis of array is equal to 1. That is what the broadcasting rule is saying, correct? So in order to broadcast, the size of the axis of both arrays in an operation must be either the same. That means size should be 2 by 2 or 2 by 2, or one of them must be 1. So 2 by 2 into 3 by 1, okay? Or 2 by 10 into maybe 10 by 1. These are the 2 rules to broadcast. And when you followed that, so in this case, when we have the shape as 3 for the rows, but there's no shape 3 for the columns, and that's where this fits in. So let's say output is going to be 385. Let's say, do we have any calculation? Let's see this one. Correct. So 1, 2, 3. So we got around, this is 3 columns. So this is actually, we didn't have any rows to this. We simply have 3 columns to this. And then when we run this, it actually broadcasts itself. So 3 into 1 is 3, 4 into 3 is 12, 7 into 3 is 21, and so on and so forth. So we know, so why this worked? Because this had one of the axes as, one of the shapes as 1, correct? So print b dot shape. Can you see this? This is 1. So there's just 1 column to here. There's one just column. There are 3 rows of data, but there's just 1 column. And since the 1 column got, so it got extended out here. I hope it's clear. So what are the other operations? So 3 into 1, 4 into 3, 7 into 4. Then 4 into 2, 5 into 4, and 8 into 4. And then 5 into 3, 5 into 6, 5 into 9. I mean, this is pretty logical because the shape has to be either the columns or the rows has to be 1 in order for it to systematically multiply. It will broadcast itself, Aparna. Yeah, it's a cross product. So it will broadcast itself. So a 3 by 3 matrix. So this is a 3 by 3 matrix will not be able to multiply by 1 by 3. So any of these things should be 1. So it's going to broadcast it. The only difference is what it did, it's 3 into 1 is 3 and 4 into 3 is 12. If it is a different way, the way you are saying, Aparna, that if it is in the row format, it's going to multiply, the values are going to change. So the output, instead of this one, the output is going to be like, it's going to be 3 comma 6 comma 9, and then it's going to be 16 comma 20. You're getting it? Comma 24. These are going to be the values for if you go it with the other way, but still it will multiply. And the last one is going to be your 5 going to multiply with the entire row. So the last one is going to be 35, 40, and what is the going to be going to be 45. So this, you can see the output for this matrix is completely different from this one. If this would be of shape comma 3, okay, if it would have been the shape comma 3, this is the output. If it is over the shape 3 comma, this is the output. As simple as that. One of the good parts that we have to see in the case where the broadcast fails. So let's see this one. When the trailing dimensions of the arrays are unequal, so this is like 4 by 3, and then the 4, it is impossible to align the values in the row. So maybe you are pointing at this part up and after looking at where the broadcast fails. So we have a 4 by 3, and this is maybe a 1 by 4. Can you see this is a 1 by 4? But this could have been a 4 by 1, wherein 0, 1, 2, 3 could have been in the rows and 1 would have been an extra column. Still it would have worked for us. I hope this is clear. So the trailing dimensions of the arrays are unequal. Broadcasting fails. So you can see this is 4 comma 1 and this is 4 comma 3, wherein the 3 and the 1 is not equal. Correct? I hope that's clear and straightforward. So the other part is indexing and slicing. So once we create arrays, could be 2-dimensional, 4-dimensional, can we slice it in an appropriate way? That is what we're going to study in indexing and slicing, then going out with universal functions. So let's start with that. Okay. So guys, what we can do is we can work on the indexing and slicing and many other interesting things which we are yet to discover in our arrays. So far we have created different dimensions of the arrays. We have multiplied them with each other. Then we converted that into different shapes of matrix. We also saw how to multiply those different matrices into mathematical operations. You can also create a string matrix, but that won't be that useful. Matrix are usually good for, algebraic purposes. And we're going to use the same for that. We can continue with other lessons as this indexing and slicing. We can work on it tomorrow along with other lessons like statistical methods, linear algebra, and NumPy, and how do we use arrays and files. Yes, correct. Just coming to that, Aparna, exactly, you're right. So maybe the example which I wrote will give an error. So what I can do is I can convert that into that dimension and I can keep that example ready. And we can evaluate tomorrow when, in which case the broadcasting will fail. Sure, guys. I hope the session was useful and informative. Tomorrow we're going to explore some more useful parts of NumPy.
Thank you so much, Suvir, for this. So before we go on, we're going to spend some time just going through interesting submissions that we've received as part of the 7 Days to Data Science Challenge. And this is to give you all ideas and insights of what type of submissions you can make. So you have time till 11:59 p.m. today to make your final submissions. And before we get there, let's just give you a very quick overview of what all concepts that we received, some of the interesting concepts that we received in the submissions. So one of the submissions that we received was really interesting. It basically said we can predict the outbreak of dengue or malaria based on using AI. And how does that work? So dengue and malaria are actually two diseases which are really related to the monsoon season. It's also related to the extent of rain, the humidity, the temperature conditions, etc. So all of that kind of has an impact on whether dengue or malaria will happen or not. And we can use basic weather forecasting, and past known outbreaks of dengue and malaria can be compared with weather data that was captured at that time. And we can use future forecasted data to actually predict if you're going to get an outbreak in dengue and malaria. So we've actually used AI now to start predicting the outbreaks. And another interesting example comes from the fishing industry. So when boats are going out to the sea, they're trying to catch fish every single day, every single morning, and they come back, either with a good catch or sometimes they come back without a catch, right? So what is happening at that moment? Now, interestingly, you can use AI over there for two reasons, right? We can use AI for making sure that when the boat comes back, it comes back with a good catch of fish. But at the same time, every time we catch fish, we actually, cause some damage on the oceanic life. So you want to make sure that there's enough breeding of the fish happening as well. So we can use AI systems that give notifications to the boats on which regions, which exact latitude longitudes to go to do your fishing. And if they go to those specific points and fish from those specific points, they will get a good catch, but we can also align it so as to minimize the damage on the oceanic environment and the ecosystem within the ocean. So we can allow breeding to happen in certain regions while good catching to happen at other regions so that there is a natural balance that is maintained rather than it being a random process, right? So as you can see, these are like really mind-boggling ideas, right? And we didn't even think about how AI could be used in these scenarios. And it's really encouraging to see such interesting submissions to come through. And I'm actually personally looking at all of excellent submissions to come from all of you who are here on the session. Do keep submitting. Let's take a quick look at I'm going to see if I can share my screen. We can take a quick look at the leaderboard at the moment, right? So yeah, perfect. Okay, you should be able to see the screen now. So if you can see, the leaderboard right now is updated till yesterday night, 11:59 p.m. So which is 14th of May, 11:59 p.m. And it has the total scores. The maximum you can score is 175. That's across if you make 7 entries. 7 entries are mandatory to be in the top positions. Our current leader for now at rank 1 are two leaders. They're currently sharing rank 1 at the moment, which is Abhishek now and Purnima. So congratulations, both Abhishek and Purnima. You're doing fabulous, right? You've actually got a full score on many of these sections of uniqueness, practicality, solution depth. This is the maximum you could score in 6 submissions, and you've literally scored the maximum. And you can see there's some differences here, like this is 28 here and 28 here and 26 here. They're kind of becoming equal. So this is also telling you where you're good, right? So both of you are actually good at creating really unique problem statements, right? You're good at giving the right solution, having the right depth of solution, which is your submission is actually deep enough to explain how that problem happens, right? And then in the runner-up, which is the second position, we have Santosh as Snigdha, right, who are basically both at the runner-up position. So congratulations to both of you as well for sharing rank number 2. And rank number 3, we have Swapna. And then we have, after that, Ananya, Jessica, Joydeep, Ashish, they're all catching up, right? And you can actually see that they're pretty close when it comes to the scores. Now, keep in mind, we don't just score 7 entries, the first 7 that you submit. We score the best 7 that you submit. So it is possible that Abhishek Roy has made more than 7 entries already, right? But we have taken the best 6 at the moment. And all of you can do the same thing if you want to stand a chance of winning. So you have time till 59 p.m. midnight. If you submit after that, it won't count, right? And we will, our trainers will make sure they rate all of the submissions before the session ends tomorrow. And tomorrow afternoon sessions, we'll announce the winners on the leaderboard. So it's really an interesting exercise that has resulted in allowing you to get a deep insight, into how AI can be used in various verticals. And the ideas that are coming out are really, really phenomenal. We'll discuss some more unique ideas in tomorrow's session when we are announcing the results. So really, congratulations to all of you, and all of you have already achieved something that's really amazing. Like, I can personally guarantee that the training that you've done here in Python, NumPy, and the one that you do tomorrow in Pandas, I can assure you, when you've completed this course, and many of you and following are religiously following this from day one, for all of you, I can assure you that you're already amongst the top 5% of data science experts in the country, because many people do not know Python and NumPy and Pandas to this level. They simply do not know it to this level. So the very fact that you've reached this stage itself means you've achieved a lot, on your own. So Varun is asking, should we have the scores today? The answer to that question is actually no. You will not get the scores today. You have time till 11:59 p.m. This board is updated till the results, which are there till yesterday night. You have time till 11:59 p.m. to make as many submissions as you want. You can submit more if you like, right? Would we have the scores for today too? No. So you will not have the scores for today. We will have the scores for today only shown to you tomorrow. So whatever you do at the moment, whatever you put at the moment will get scored by tomorrow afternoon, and we will announce the final winners before the session ends tomorrow. So all the best to all of you, and I assure you, you're all phenomenally good when it comes to data science. Most data scientists in this country are not able to come up with solutions to problems. Like, they're not even able to imagine how AI can be used to solve certain problems. And you are doing that. You're doing a phenomenal job here. Programming is something you can learn. If you don't follow the video, you can always go back, relook at it. You can always Google stuff. You can learn the programming syntax. It's not difficult at all. Figuring out where to use what AI model is the toughest part, and that is what we teach in the 90 days program. So congratulations to all of you for actually being in the top 5% of data scientists in the country already. And we look forward to some really fabulous submissions to come from you till 11:59 p.m. today. And then tomorrow we announce the final winners, and the final winners, top 3 final winners, receive a free pass, complete free pass to the entire 90 days program of BlobCity. And this is over and above all the learning that you've got in actually following this exercise. So thank you so much. Thank you again for spending the evening with us, your afternoon with us. And we look forward to connecting with you again tomorrow at 11 a.m. sharp. We'll begin dot on time at 11 a.m. tomorrow. So thank you and have a lovely evening till then. And stay safe, stay at home, and see you again tomorrow.